Welcome back. Today we'll cover t-tests of the difference of two means. In some ways this may seem like a step backward to you. After all, we already covered regression and learned how to use dichotomous independent variables, as long as we had interval level dependent variables at least, and we learned to interpret those results. And in fact, that's very close to the truth. T-tests are a special case of the general linear model, the y equals b0 plus b1x1 and so on. You've already used critical t-values for test statistics when samples were too small to invoke the central limit theorem, so you couldn't use z-values. And though you may not have realized it, we've also been using t-tests to evaluate the significance of your regression coefficients. What the t-statistic is a standardized measure comparing an observed difference to an expected difference, or an observed association to an expected association. That is, its basis is a difference of differences between what we see in our sample and what the null hypothesis predicts. I'll use the language control in experimental groups to describe x equals 1 and x equals 0 and x equals 1. Control is 0, experimental is 1, for the two levels of an independent variable that's dichotomous. That doesn't mean you can only use this with experiments. It's simply a common vocabulary that's come up because experiments are one of the most common uses of t-tests. So let's take it apart. Like most standardized measures, the actual t-statistic equation has two elements. First, the numerator, the top, represents the raw magnitude of the difference as observed minus the expected difference. That is, x bar 1 minus x bar 2 minus x hat 1 minus x hat 2. That's the means you observe versus what you would predict based on your expectation of your null hypothesis, much like a chi-square test. Now, very often the second term, the expected difference, is 0 under the null hypothesis. If we compare the observed difference to 0, then it simplifies the numerator to just the difference between the means, x bar 1 minus x bar 2, the observed difference. The denominator then, on the bottom, provides the means of standardization, so t-scores can be compared to a known distribution, specifically the student t-distribution, as you might have guessed. The denominator is the standard error of the difference, and it produces a statistic with a familiar interpretation. The t-value for a difference in means is simply the size of the difference converted from the original units to standard errors. That is, a t-value of 1 would mean that group 1 had one standard error higher value than group 2. So the t-score thus provides a way to use null hypothesis significance testing with categorical independent variables. If they're placed in a bivariate regression, the constant is the mean of the control group, and the magnitude of the coefficient, that is b1, for that binary independent variable, is the difference between the mean of the experimental group and the mean of the control group. That is, we've come full circle in terms of the linear equation. Our t-test is actually exactly what we've been doing in linear regression, but we've talked about it and thought about it differently. Our predicted y then is the mean of group 0 plus the difference in means times the dummy variable, which comes out to, if it's just those two variables, if it's bivariate regression, it comes out to predicting the mean of group 0 for members of group 0 and the mean of group 1 for members of group 1. So to go back over that, because we're going to expand on it, it's helpful to think of this in terms of each possible combination of independent variables. For a bivariate model with two categories, if x is 0 in the equation, b1 drops out and leaves us with just the constant. So for every case in the control group, the mean y value of the group will be our best guess. The same holds true for the experimental group. Our best guess is the group mean of the experimental group, which leaves us with the prediction equation, group 1 mean equals group 0 mean plus b1 times the indicator for group 1. Rearrange that to b1 times the indicator equals group 1 mean minus group 0 mean, and since the indicator is 1 when it belonging to group 1, the equation for those in group 1 is B1, that is the coefficient, is the difference in group means between group 1 and group 0. Now, returning to the t-value equation, if group 1 has a higher mean than group 0, t will be positive. If group 0 has a higher mean, t will be negative. But when we're using a critical values table, you'll only see the positive values. Instead, you need to compare the absolute value of t to the critical value. So if your critical value is 3 and your t statistic is -4, then you would reject the null hypothesis. Now you're still using a linear model, so linear assumptions apply, particularly regarding homogeneity of variance. Although, as usual, there are ways to find more robust statistics. Now there are two little changes you may sometimes see to this type of t-test. First, there's no mathematical reason the expected difference must be 0. For example, you might be interested in whether the difference in income between males and females is the same in the populations of legal and illegal immigrants in the US. In that case, the gender difference in legal immigrants might be the expected value under a null hypothesis of no difference. The numerator of t would then be the mean male income for illegal immigrants minus the mean female income for illegal immigrants minus the same but for legal immigrants, that is, a difference of differences. Everything else is the same until you get to the interpretation, at which point you just need to be careful that your reporting reflects the hypothesis you tested, since it's somewhat more complicated than a typical t-test. Now the second tweak you might see is a special case of the first called a paired samples t-test. In some situations, comparisons are made between means of a variable under different conditions for the same people. For example, if we sent resumes with different ethnicities of names to the same set of companies, so the same human resources people were looking at them, we would have a paired sample of responses, or ratings. The difference of differences model above reduces to a simple difference of means in the case of paired samples and looks very similar, except that the standard errors can be calculated using the case level differences, and so they're usually smaller, because by pairing them within a case, you eliminate the variance between cases when you're comparing the difference. Now, in SPSS and other software, you may see multiple options. You may see one sample t-test, paired sample t-tests, or independent samples t-tests. The first compares a mean to 0 or another specified value. So, for example, if you know the mean of a group from a previous paper that reported it, but you don't have case level data on it, you could still use a one sample t-test. The second compares two sets of results for the same cases, again paired samples, and the third, independent samples t-test, compares two empirical groups like men and women. As long as you can remember which of these is which, the small differences in calculation can be left to the computer. So to recap, t-tests are used to compare means to each other or to a value. The t-statistic is equal to the observed difference minus the expected difference under a null hypothesis, all divided by the standard error of the difference. There are special cases of the general linear model, and the results for an independent samples t-test can be replicated exactly using bivariate OLS regression. Don't use them when you want to test for association between two categorical variables. As a reminder, that's what chi-square tests are for. But that's basically it. Anytime you want to predict an interval level variable with a binary independent variable, you can either use bivariate regression or t-tests, and they'll come out the same. Now, in the next couple videos, we'll take our logic a little further. We'll extend how we can use these models by using linear regression to model multiple categories of a single independent variable, and by using it to simultaneously model multiple categorical independent variables. Thanks for watching. See you soon.